we're going to look at some reactions of alkanes, and one of the most common ones that you've probably met is candle wax. So it's present on the camera there. This is a very large one, which is why it's solid at room temperature. We expect alkanes to be liquid or gases at room temperature because they're non-polar, so they have weak forces between the particles. However, wax is such a large alkane, there's a much higher probability of temporary dipoles, so there's more forces between the particles. Also, the molecules kind of tangle up a bit like spaghetti, which helps hold them together better as well. By the way, solid wax will not burn. Okay, it actually can't burn until it gasifies. So the wick is required to actually heat it up enough to break enough of those bonds to turn the wax into a gas around the wick, so that can burn. And the heat from that will cause more melting, which then allows more evaporation, so it allows the candle to keep burning. Another one we're going to use is a liquid called cyclohexane, and cyclohexane is really useful for us. The problem is it's really bad for us too. So that's why we're working in a fume cupboard today. It's not a good chemical to play with if you're worried about your own safety. The first reaction I'll look at is where I'm going to set some cyclohexane on fire and then set some wax on fire. So we're looking at combustion. I'm not going to put too much on there. You'll hopefully see why I'm being conservative when I light it. With a match that actually is lit. Always the fun thing, trying to light something in a fume cupboard. I didn't even touch the liquid to let that catch, by the way, which is another thing that shows that it's the vapour just sitting above it that's catching fire. You see it's quite a dirty flame. That's not because the tin lid that it's on is dirty. It may have some effect, but not a lot. You'll see a lot of soot coming off it. It's not a clean combustion. Alkanes don't combust completely because the carbon-carbon bonds are very strong and there's not enough oxygen in air to allow it to completely combust. So when you're doing an equation for the combustion of an alkane, you tend to have carbon monoxide or soot as one of your products. You couldn't see the carbon monoxide in there because it's a colourless gas just like carbon dioxide, but we sure as heck could see the soot, and the yellow or orange flame is another giveaway that it's incomplete combustion. It's not giving as much energy as you would expect for complete combustion. Alright, just to sort of reinforce the point, we'll light a candle. And you'll see that that also is not going to give a completely colourless flame, a blue flame. I'm sorry I'm lighting that out of screen, but the fume cupboard's putting everything out. So, alright, and so what we're seeing now, we're starting to see the alkane burning. To start with, just the wick. But now we're starting to see that burning. If we leave that, I do intend to leave it burning for a while, you'll see of course that it will melt. So there's enough heat energy in that candle to break enough forces between the molecules to turn it from solid to liquid, and then from liquid to gas, and then it's the gas that's going to burn. Alright? So one of those common misunderstandings is that generally a liquid won't burn. It is actually the gas, the vapour sitting just above it that's catching fire. So if you had an ethanol flame or something like that, it's not actually the liquid ethanol that's burning, it's that little bit of ethanol vapour that sits on top. A petrol flame, this is why smoking would be a stupid idea, but lighting any flame in a gas station is a dumb idea because there's so much petrol vapour around. Some of you will probably know if you're sunburnt and you go to the petrol station how much it stings. It's because the petrol vapour, which is another alkane, the petrol vapour is actually basically attacking your skin. That's why it stings so much when you're sunburned. Okay, the other reaction that I really want to look at today is, this is cyclohexane again, and I'm going to add a chemical to it called bromine water. Bromine water is just Br2, dissolved in water, so it's not quite so fumey and dangerous to use. It's still pretty nasty stuff, so I'm going to use it in the fume cupboard. Like chlorine, it can do serious damage to your lungs, so we don't want to get it out of here at all. Now, bromine water, when I put it in here, should make a second layer. The reason for that is the bromine is an aqueous solution, so it's dissolved in water, whereas cyclohexane is non-polar, so the two don't mix. Non-polar solvents will only dissolve in non-polar solutes will only dissolve in non-polar solvents. This is non-polar, this is polar, so they're not in a mix. I probably take it safely out of here. You can see there's nothing much happening. Okay. If I give it a good shake and let the two layers mix, and make sure I expose it to light, then we do start seeing something happening. The first thing we're going to notice is the bromine is being drawn up into the higher layer here, and you can see that by the colour difference. Now if I expose that to natural light, so the ultraviolet part of natural light, for about 10 minutes, this colour will start to fade. And the reason for that is a substitution reaction. So substitution in sport is where someone is taken off and then someone else is put on in their place, yeah? Same thing is happening. In this top layer here, and it will take a while, it won't happen in the length of this video, hydrogen atoms are being removed and bromine atoms are being put in their place. So it's removing an atom to put another one into place. So it's what we call a substitution reaction. So what's happening here is we're making bromocyclohexane. That means where's that hydrogen atom going to go? Well, it binds to the other bromine. This is Br2 is bromine. It binds to the other bromine to make HBr. HBr is an acidic gas, another reason for doing it here. So if I had damp litmus paper and put it over the top, I would expect that damp litmus paper to turn blue. The problem is the reaction rate here is so slow that there's no point doing this on the video because you won't see any effect. It takes about 10 minutes. The reason I'm showing you this reaction is it's often used to tell the difference between an alkane and an alkene. Alkenes have a very, very different reaction to the alkanes, so we use bromine to tell the two chemicals apart.